So good morning everyone. So this is lecture number 2 for differential amplifiers topic, which is belongs to analog circuit designing. Mainly we are focusing on BJTs, and last lecture I have told that whatever the things I am teaching right now, it's from one book called Behzad Razavi, and the book title is Fundamental of Microelectronics. So let's review the last lecture, what we have studied. So we have studied bipolar junction transistor at the circuit level, not at the device level. We have studied that. We have made the IV characteristic. From the IV characteristic, we found out what are the different region of operations are there for BJT. In that, we found out saturation and active mode of operations are the one which are basically BJT is following, and cutoff is the one when base to emitter and base to collector junction both are reverse bias. And there is one more mode of operation is there, which is called inverse mode of operation, which is not happening generally in BJT. And as we know that we want to make our BJT in the amplification mode, or which can give you the gain, voltage gain or maybe current gain or whatever the gain you want, then in that case you need to keep your transistor in active mode of operation. So when I'm saying transistor, it means that I'm talking about BJT. And we talked about input and output characteristic, where it was current versus VB, means collector current versus VB, which was an input characteristic. Then VC versus IC, which was the output characteristic. And through that we have found out different region of operations, and we understand that everything will work very smoothly if your transistor is considered as one of the ideal device. But if your base width is not ideal one, and it's actually smaller, or maybe it's not the way it has been made, then you will see some slope in the active mode of region, and that slope is going to give you 1 by R0, and that's R0 is deciding the base width modulation resistance, and this whole effect is known as early effect voltage. And we have learned that for a different VB your characteristic is changing, and for different slopes, if I extend them at the negative side of my characteristic, so it's touching at minus VA point, and that minus VA point is known as early effect voltage. So this is the thing we have learned. Thereafter we found that BJT is, although ideal, it's a non-linear device and it has two junctions. What we want to do it to make it more easier, so there is something called small signal model we are going to make. So small signal model we have derived using two-port Y parameter network. Same thing can be derived for H parameter, or it may be derived for Z parameter, or maybe ABCD or S parameter. All should give you the similar answer, but the only thing, when we are using the Y parameter, I am concerned about how much easily I can use that as a tool to find out gain, to find out input impedance, to find out output impedance, and to find out different poles and zeros associated with my amplifier. That's why it's very easy. This is the reason why I like Y parameter. And similarly, like as I told, all new engineers who are in this era, they are following Y parameter. So if you look at some old books, they are still following H parameter, but new books such as like Behzad Razavi, he is following Y parameter. And after that, we understand that this small signal model or the small signal gain can be achieved through the two-port network understanding, but before that my transistor has to be in active mode of operation. So if it is not in active mode of operation, you will not get the amplification. So this is what we wanted to do, and for that we learned that how to bias my BJT. Biasing the BJT means I am giving the appropriate value of DC such that transistor is in active mode of operation, and on top of that DC I am going to give my AC signal, or you can call it some input signal. It may be speech signal, it may be some signal coming from antenna, it may be any signal that you want to get amplified. So that is what we are doing with the BJT, and for that we learn different techniques. Those techniques are actually evaluated through one thing which is called PVT independency. So your circuit should not be process dependent, voltage dependent and temperature dependent. When I say process dependent means your circuit should not give you wrong answer or the unexpected answer when the transistor is changing. Means it should not be depending on the manufacturing quality of BJT. Like we know that BJT's beta is varying from 50 to 200, or it may be more than that, sometimes it may be lesser than that, but still my circuit should be giving me the desired answer. Moreover, we know that voltage is also one of the key factor, and it's playing the role in getting the amplification number. So it should be independent of voltage as well. And similarly, my circuit which I am making, it should be workable at minus 40 degree, or it should be workable at 0 degree, or it should be workable at plus 125 degree. So all the industry people, those who are making any product or giving you any product, so they are checking the whole circuit from minus 40 degree to plus 125 degree, and then they are quoting the worst case number, and that worst case number is like they are going to tell that this is the performance of my circuit. So this is how it does. They are not quoting the best case, but this is the worst case. So this is how we have to ensure that whatever we are making, that has to be PVT independent, and for that we found out some techniques like technique 1, 2 and 3, and at the end we found out that emitter degeneration technique is the base technique, which is giving you the linear relation between input and output. Your collector control current is better controlled through the input side, means VBE side. So those things can be done, but this was for the biasing of the circuit. Once you do the biasing and everything is done, your next job is you have to give the input, and that input is the one which you want to get amplified. Now this input, when I am connecting through function generator, I learned that look, if I go to laboratory, most of the instrument will have some input impedance and output impedance, and my function generator's output impedance is 50 ohm from where I am taking the output, and that 50 ohm is actually loading my DC circuit. I was expecting some voltage which is the voltage divider coming from R2 and R1, but instead of that I am getting something else. So for that, what should I do? I should keep one big capacitor, and the role of this big capacitor is blocking the DC which is coming from the top side. Top side means VCC. So you should stop that current, DC current coming from VCC side, and it should not be shared by my 50 ohm function generator, and that is how we kept a big capacitor. So this was one thing we learned. And now what is today's agenda? So now slowly model, now these two are the key point to understand what is single-ended amplifier, what is pseudo differential amplifier, fully differential and differential amplifier. So all four names maybe you have heard, but what are those and how to implement them, this is going to be taught today. Then one more thing, like when you are using a single-ended and differential amplifier, single-ended has some number of components. Let's say single-ended will have X number of components, then differential will have the exactly 2x number of components. So everything is getting doubled. So if we are making my circuit twice, or I am doubling the area, then what should be the advantage of differential over single-ended? So that has to be understood, and that is the part of today's lecture. And there are slowly we will move to fully differential amplifier. What is a fully differential amplifier? And at the end of this lecture, we are going to understand what is small signal differential AC gain and how to derive it. That is what agenda of today's lecture. So now let's start from the point where we have started. So my circuit, if it is common emitter amplifier, which is having resistor as at the tail of emitter, or you can say that it's emitter degeneration circuit. And I want to connect VCC over here. VCC is some voltage, let's assume that it's 2.5 volt. But this 2.5 volt is coming from bridge rectifier, whose role is to convert AC signal to DC. So this DC signal which is available here, it's coming from some AC signal which has to be stepped down and whose input is 220 volt 50 hertz. This number I wrote it for Indian system, this 220 volt and 50 hertz. So you are stepping down the AC voltage to some value whichever you want, and then I am using the bridge rectifier which is going to give me signal which looks like this one and having the ripple at something like 50 hertz because my input is varying with 50 hertz. So this is the input I am giving. Instead of giving accurate DC, or we can call it the exact DC voltage, I am giving pulsating DC. This is not a good thing because this DC has some AC. So one technique I told you yesterday, that you connect a big capacitor. That capacitor is known as decoupling capacitor, and the role of this capacitor is it allows all the AC signal. So from here all the AC signal will be grounded, means this ripple will be grounded, but the DC is not going to grounded, or it will be blocked by this capacitor, and this DC will be applied to my common emitter degeneration circuit. So this is what one way to remove this ripple, but you have to use very big capacitor. It has to be outside this box. But if I ask you, do not do anything, and if this is the circuit I want to design and I want to make this circuit in a chip, let's say I want to design a chip. Inside this chip there is a common emitter circuit and I want to make everything on chip, means I want to design something which is inside this red color, then what could be the solution? So the solution maybe we can like understand from these diagrams. We have like this 110 volt 60 hertz, it's American number. So instead of that you can consider 220 volt 50 hertz, as it has been taken from Behzad Razavi. So he is using 110 volt 60 hertz, but that is not the case for India. For India it's 220 volt 50 hertz. Then there is a transformer, step down, then this is the rectifier, and this is giving you VCC signal, and this is acting as a ground, and this is a mic. This part looks like a AND gate, is a mic, and then there is a AC coupling capacitor, and this two bias circuit means there are two resistances which is giving the DC voltage required for Q1. But here what is happening, I am getting AC signal which is speed signal, which is something like this. My speed signal looks like this one, let's say, when I am speaking. This is my input coming from mic, and at the output I'll get little bit amplified signal, of course, but the amplified version of this one will not be the case, but it will have something called VDD also, VCC also playing the role. When I am saying VCC, VCC is looking like this one. So your output will be like this. So it's blue colored is the amplified version of the input, and it's riding on the AC signal or the AC ripple coming from VCC side. So it's not a good thing, and that's what drawn here. If you look at this thing, you can see that it's having some ripple, and that ripple is coming from VCC. And if you're looking at the path, there are two paths. One is signal path and one is ripple path. So ripple path is coming from VCC and signal path is coming from the gate, or it's coming from the base. So this is what happening here, and it's very important to remove this kind of error, because otherwise you are going to see those things as output and it will disturb them. So how to remove that? So before removing this, let's understand. Okay, so as the topic of our discussion is differential amplifier, so I am giving you like direct answer that it's a differential amplifier. But before understanding this, the answer is differential amplifier, why we are using differential at all. So let's understand differential amplifier, different topologies. So those topologies are, one topology is single-ended amplifier, another topology is pseudo differential, third one is differential, and fourth one is fully differential. So when I'm saying it's single-ended, it means that I have one input and one output. This triangle symbol denotes amplifier. This antenna symbols denotes your supply voltage. It may be plus VCC, this is maybe minus VV, and it's with respect to ground, and this is with respect to ground. This is V in and this is V out. So it's clear that you've seen this kind of circuit already, that all the common emitter amplifier, everything we have studied in lecture 1, all things were single-ended. You can highlight them as a single-ended. But now when it's a differential, means pseudo or simple differential or fully differential. Wherever there is word called fully differential or pseudo differential, all means that I am going to give the input which will have basically two inputs, one plus and one is minus, and both will have a phase difference of 180 degree. If I am doing this, this is going to be called as differential input. And how does it look like? It look like this one. This amplifier has two inputs. One is sine wave, another is also sine wave, but both have to have 180 degree phase shift. So how can I do that? If I am applying one side a sin omega t and one side if I am applying minus a sin omega t, of course there is a difference of 180 degree. So this side if I apply my plus V in, and if I apply minus V in, so effectively you can see here I kept intentionally minus sign this side. So here its available voltage is minus V in and here available voltage is plus V in. Right now I am not talking about DC, and I am assuming that DC is available from somewhere and it will make my transistor in active mode of operation. So let's put it in that way. So this is what if we are going to give, then it's coming under the class which is called differential, and it may be anything like pseudo differential, differential and fully differential. So let's define those things. If you have two inputs and one output, two inputs, one output, then it may be pseudo differential or maybe differential. But if it has two inputs and two outputs, then it's called fully differential. And here when we are talking about pseudo differential and differential, how to distinguish both of them? When it's a pseudo differential, I mean to say there are two circuits. Let's say these are the two circuits which we have studied just now. If we are having two circuits and both are connected through, one is V in and one is minus V in, and there is no relation between two circuits. So circuit 1 and circuit 2, they are not interacting to each other, they are not uh, loading to each other, their current is independent, their voltages are independent, everything is independent, but my inputs are differential. When I am saying differential means I am giving 180-degree phase shift. If that is the case, then we are going to call it pseudo differential. I am repeating again, when it's a pseudo differential, it means there is no relation between two circuits. There is no relation, or they are not disturbing each other. That kind of circuit, if it has input of 180-degree phase shift, we are going to call it pseudo differential. But if there is some interference or the current or those things are, let's say I am giving you one example, which is differential. So differential means sine wave which has 180-degree phase shift. Let's assume that there is, so if this is R1, R2, it's the same circuit, but this resistance I kept it with tying two emitters together, and now what is happening, this current and this current are actually depending to the current flowing through this one. So it has a relation. This circuit is not independent of this circuit. Both are interacting, both are depending on each other, and this kind of circuit, when there is a relation between two circuits, we are going to call it differential circuit. So if there is a relation, it's a differential. If there is no relation, it's it's pseudo differential. If it's one input and one output, then it's a single-ended. And if there are two inputs, and if I take the same circuit and take the two outputs, which is one is plus and one is minus, then this circuit is known as fully differential. Fully differential is the one, there are two inputs and two outputs. This kind of circuit is known as fully differential. So all names, but fully differential will have, or any differential will have a input of 180-degree phase difference. So this is the main tagline, we should understand that first. Now let's go to the next part. Look, we categorize this structure in 4 different parts, but why do we prefer differential over single-ended at all? So one technique may be to remove the VCC noise which was coming, but still it's not justifiable. Look, one for doing that thing only, we could have used one big capacitor to kill that noise which is coming from the input side or from the rectifier side. We could have done that, but if there has to be something else because of which differential is very popular than single-ended. So I'll give the answer of that first, and then I'll tell you how to transform this any single-ended circuit to the differential network. So now let's go to some circuit. Okay, so let's assume that this is a black box which is differential circuit. It may be single-ended or okay. So it's fully differential, two inputs, two outputs, y1 and y2, two inputs, two outputs. And I'm putting one battery over here so that this battery will make sure that my transistor, which is a part of differential amplifier, it will be in active mode of operation. This is what we want to do, and this is some voltage, DC voltage. But look at this DC voltage very carefully. If you look, if you are looking at the path, it's actually, if you remove this AC and if you look at just DC path, same DC is available both the side. So now I am defining new quantity. This DC voltage is common to both the inputs. This DC voltage VDC is common to both inputs. Okay, this is if it is known to me, I rename this VDC as common mode voltage because it's common to both. And generally this common mode voltage is DC generally, but this is not true for all the cases. It may be sine also. I can give sine, and through sine also I can bias my circuit. This is also possible. But generally, in general case, we may have common mode voltage which is DC, but still you should remember that it's not the case for every time. It may be different. Sometimes it will be AC also, but still it's common to both. So still that AC voltage can be known as common mode voltage. Okay. So this is we understood, and here there are two inputs. One is, let's call this one as x1 and this one as x2, and we know that in linear equation this is going to happen. Let's make it small letter so that it's AC quantity. So this is what we are expecting, where y is output, x is input, and c is initial condition. Y is output, x is input, c is initial condition, and m is slope. If we want to mimic this equation for our case, then what will happen? This is my output voltage, this is my input voltage, this is my common mode voltage. I am keeping it with the subscript called Cm. If I add one more I, it denotes that I am talking about input common mode voltage, and the slope is a gain. So this is going to happen, and you can write equation for your case also. So let's write the equation for our case. What I mean for our case is that if there are two inputs, one is x1. For x1, this may be the case that you have C, but this is the ideal case. But if there is nothing like ideal thing in the world, and you will have something called harmonics. If you remember the circuit when we started, yeah, this circuit has a ripple. Ripple may have another word. I can, instead of ripple, I can call it harmonics also. Harmonics, when I am saying harmonics, means it has some frequency components. It may be F, 2F, 4F, 3F. So those harmonics are there. So you can see here, those harmonics are affecting my VCC. So similarly, in this circuit, if your input is fine, it's A sin omega t, but the circuit has some inherent property, it's not completely ideal or it's not completely linear, but when we are solving it, we are doing the piecewise linear, that's why it's working. But if you are doing the piecewise linear, and in that case you should follow this equation. But if it is not piecewise linear and it's a real circuit, then you should see the non-linear component. And when I'm saying the non-linear, means you should have something like this, that m1 x1, then m2 x2 x1 square, m3 x1 square, m4 m3 x1 cube, m4 x1 raised to 4, and so on, plus my common mode voltage, which is C. Let's call this one as VCMI directly. Similarly, for Y2, you can write down it's m1 x2 plus m2 x2 square plus m3 x2 cube plus m4 x4 cube, sorry, x2 raised to 4, and so on with VCMI at the input. Now we know that we are interested in a differential circuit or the fully differential circuit, which has output, and it can be found out by y1 minus y2. As we have applied x1 minus x2 as an input, we can apply we can get the output, which is y1 minus y2. So if you do y1 minus y2, that quantity is equal to, you can see, okay, before doing this I should put, let's replace x1 with Yeah. So I want to replace x1 with V in. So let's put it this way. My x1 is V in and my x2 is minus V in. So x1 is V in and x2 is minus V in. You can put it this way. So all these are numbers are positive. But here in this case, okay, yeah. So there won't be any change. Here it will be V in square only. But for this case, it will become minus V in cube. For this case, it will remain plus, and so on. You can solve the rest of the series if you want. And if you subtract both of them, what you are going to see? You are going to see 2V in times M1 plus, if I subtract this quantity with this quantity, I am going to see 0 plus 2V in cube times M3 plus 0 and so on, and your VCM I is also 0. Let's give this different number, a different color. Okay, so from this thing you can see that when I am solving this non-linear equation and I am subtracting both of them, wherever there is a even number of terms are coming, or wherever there is a whenever I am putting even V in x2 equal to minus V in, the polarity is not changing. Those are getting subtracted and at the end they are becoming 0. So those quantities are all the even harmonics or all the even terms are going to 0. This is one thing. One more thing, DC value, or do not call it DC. DC is not a, now if we are in differential amplifier we will call it common mode quantity, or the common mode voltage goes to 0. So if your signal which is DC, and DC has, let's say you wanted to give this one as a DC as input to your circuit, then even though there was some distortion, those distortion will be like nullified when I am using differential circuit, or I can call it that the common mode noise will be 0. So instead of this one, the common mode noise will be 0, and I can same time I can call that even harmonics will be 0. So if you look at my analysis, you can see that even harmonics are 0, and when I am saying it has a better noise immunity, means the common mode noise is also like very good, like it's removed, so there is no noise coming from DC side, so better noise immunity. So these two are the main property of differential amplifier, because of which we don't hesitate to even increase the area. So this is one thing. Now let's say that if I want to transform my single-ended to differential, how to do it? So there is one circuit. Let's say, how do I know that whether they hear they can see and what time they were with me? Okay, so I got like this confirmation from our admin. He told that you were with me till this analysis. If you are using the differential amplifier, your even harmonics goes to 0 and your common mode noise goes to 0. So this was the question I asked when I started the lecture, that why we are using differential amplifier at all. And if we got the answer, then the next question was how to transform this single-ended amplifier to differential amplifier, or maybe pseudo differential, because at the first hand let's learn how to convert single-ended to differential, and this is one of the circuit I gave to solve as a illustration. So let's put this circuit: resistor, inductor, capacitor, and there is a resistor. I kept it some random thing here, but how to convert it to pseudo differential? So this was the circuit with V in and this was the V out. Now I want to convert this to differential. What I am supposed to do? I have to put the same circuit. So let's make the same circuit which is look-alike to this one. Let's call this one as V out plus with respect to ground, and this one as V out minus. So I'm drawing the same circuit, which is this side. I'm replicating that circuit to this side. Same component, same values, everything is same. And I'm calling this one as V in with respect to ground, and this one I'm calling minus V in with respect to ground. And if I draw this circuit one more time, just to make it beautifying it, same thing, what I can do, or maybe if you like, you can, for the simplification, all the simplification, what we can do, so this is the way to convert my AC or single-ended circuit to differential, which was look like this one. First part, you have to make the same circuit in a such a way that it's a same circuit, all the components values are same, everything are same, just you are copying it and you are giving the input as differential. Now let's take another circuit. So just to make you comfortable, I thought like this technique works for every circuit. I used another transistor called FET. FET look like this one, but do not worry, it's not so much difficult to understand. If you can understand BJT, you can understand FET as well. So if there are two transistors M1 and M2, this is VB1 and this is V in. If I want to transform this circuit to differential one or the pseudo differential one, what do you have to do? You have to copy both the things, both the side. So M1 and M2 both are same, and this side it's input, this side also input, but both the inputs are 180 degree phase shift. So both are V in, but both are 180 degree phase shift. So this is differential circuit. Similarly, if you want, we can take one more BJT circuit. If this is the circuit with you, if I want to convert it to pseudo differential, what I'm supposed to do, let's call it R1, R2 and this as RC. If I want to make differential, I have to make the same circuit. This is very easy, but sometimes people has doubt. How does it work? So this is C, this is minus plus, this is V in, and this is V in. So it's 180 degree phase shift, and yeah, so this circuit is pseudo differential. What we are converting right now, it's pseudo differential. So how to convert single-ended to pseudo differential? We know that. And whenever there is a differential word is associated with your circuit, you should do one thing. You should add 180 degree phase shift between the inputs. So this is the main underline you should remember. Whenever there is a differential, means input has to be 180 degree phase shift. Whenever it's a differential circuit, there are two blocks. Both blocks are identical. Both blocks are identical. Okay. Maybe this, both blocks has to be identical. Means this transistor and this transistor Q1 and Q1 both has to be equal. This RC and this RC has to be equal. This R1 and this R1 has to be equal, and this R2 and this R2 has to be equal, and this capacitor and this capacitor has to be equal. I'm telling this because the performance coming from all the second harmonics, fourth harmonic, sixth harmonic, all even harmonic should be coming same, so that it can be nullified. Otherwise you cannot get the even harmonics removal. If you want to have the even harmonic to be removed, then you have to make sure that all the components which you are making are exactly same. If they are not, then you cannot achieve even harmonics reduction or the nullification. Okay, so similarly you can make other circuits. I am not wasting my time in other circuits. So let's go to other part, and it's very interesting analysis. So when I was I was trying to understand the circuits, this is the better idea to understand. Let's say you have two balanced network, because we understand, okay, before telling this I should say that any circuit I am going to use, it will have two things, one sine and one DC. DC is common mode. Common mode input voltage takes care that this circuit has some BJTs, and those BJTs will be in active mode of region. So that can be only done by input common mode voltage. Inputs are the one which are going this way, or you can say that 180-degree phase shift, and I am taking the output from this side. This is differential. So whenever there is a differential amplifier, there are two possibilities. One possibility is that, let's remove these two. When you are only doing DC analysis, then there is no AC sources, because I am assuming that my circuit is still linear. Linear is the one which follows the superposition theorem. So as per superposition, if there are multiple sources are available, I can treat them one by one. So when there is a DC source, I am not going to treat AC source, and if AC is available, I am not going to treat DC source. And one by one I am going to check the output, and for them I am going to add both the things like AC and DC, and ultimately we are going to tell that this is my total output using superposition theorem. So this is what we can do. That's why we are following this way. So there are two possibilities. One possibility is that you have only AC inputs, and there is one more possibility that you have only DC input. So let's assume that there are two blocks. These two blocks are the single ended. It may have different thing like inductor, capacitor, whatever you want to put it, let's put it. Same thing you have to put it here, because we learned that if you want to transform your single ended to differential, you have to do one thing. You have to put two blocks identical to each other, and the input which you are giving here has to be 180-degree phase shift. So that was the first possibility. When I am adding my input, both has to be differential, means this way. And I told you that this is not pseudo differential, it's differential. And differential circuit is the one when both the blocks are connected to each other with some link, and they are going to disturb each other, or maybe your circuit will be robust enough so that one balance block will take care of the another balance block, and your output will be PVT independent. This is what we want to do. So I am connecting these two balance block with a link which has a voltage called Vx, Vy, Vz, Vw, or maybe Vb, something. All these voltages are available. And if I apply voltage as this side V in, this side minus V in, and both are identical, then what is going to happen at Vx? Look, if you look at carefully, you understand that the current flow will be in this way, right? Because this is negative, so it will be, current will be one side it's synced and one side it will be sourced. And if I'm looking at the voltage over here through the multimeter, I'm going to see the 0 volt. But this is happening only because of I'm applying this side V in, this side minus V in. That's why I'm seeing that link voltage as a 0 volt. And this 0 volt, we are going to call it virtual ground. And this virtual ground is happening at the signal which is AC by nature. Or you can say that it's a 180-degree phase shift, but still it's AC, and we are going to call or rename this one as AC virtual ground. So if there are two balanced network and they are connected by link, that link voltage will be giving you ground potential, and we are going to call it AC virtual ground. It's only happening in this condition. Remember, if your inputs are not 180-degree phase shift or not minus of another one, then this is not going to happen. This is only going to happen when its application of input is very important. Now there may be, so this was the first case when you are applying the AC. The second case is the one, now I am interested in DC. I want to give the DC voltage. What I mean by DC? Just now we have learned that DC is renamed, or it has been given one more name. It's called common mode because it's common to both. Common mode means inputs are. So for this circuit, similar to balanced network, so balanced network 1 and balanced network 2 both have same number of components, transistor, inductor, capacitor, resistance, everything are same, and both are identical. There is no change, and they are connected by a link, same like the previous one, all with the name Vx, Vy, Vw and Vz, and I am giving the input which is common, or you can say that both sides it's voltage V and voltage V here, VCMI, VCMI, input common mode voltage. So what I am going to see here, you cannot tell anything about first of all voltage. What you can comment about it's the current. So if I put one resistor here and check the current will be double. This is what I can see. So in this case, this Vx potential is not going to be virtual ground. There is no virtual ground. It's virtual ground in the only one case, when it's AC signal you are applying with 180-degree phase shift. If you are applying same voltage, still it's wrong. You will not get the virtual ground, and this is the place where people are making mistake. So we understand two things. If you are applying AC, it's a virtual ground, and if you are applying DC, common mode voltage, you are going to see the two current, and those two currents will give you double of current at the resistance at the link voltage. Yeah. The problem we have started with, our problem was, if we have a circuit which is supplied by VCC, and this VCC is coming from rectifier and the transformer circuit or the step down circuit. My VCC is not exactly DC value, it will be the pulsating DC. Then what could be the solution? One solution was, I can connect a big capacitor op chip, and that big capacitor will remove all the noise coming from VCC. But another solution, I told you at the beginning itself that differential will be one of the solutions as we are studying the differential amplifier. So what we have to do, you can keep the same circuit at another place. Just look at this part, like V out plus side, you have one circuit, same circuit I am connecting to V out minus side, and this V out plus and V out minus, if I am subtracting both of them, you can see that initial voltage or the common mode voltage, so as we agreed that Where is that analysis? Okay, yeah. So as we agreed that your common mode noise or the DC value is going to be removed. So same thing is happening here. The DC value which is donated by VCC, actually it's a common at the V out plus side and V out minus side, and when you are subtracting, that will be removed. So this is what it has been drawn in another side with some triangle, and it's a differential amplifier, it's subtracted, so that will not be there. Okay, wonderful. So now let's talk about some more thing like input to the differential structure. If I am giving this kind of thing, like my input is one side is a sine wave, another side it will be minus sine, or it's 180 phase shift, and at the output we should see the 180 degree phase shift. So there are two cases. One circuit, left side circuit, has common mode sine wave as an input, and you can see the output is also varying with respect to input. So it's in the phase, x and y both in the phase, or you can say that both are same. But when you are giving the 180 degree phase shift, or you are giving the differential input as an input to the differential structure, your output will be also differential. You can see that the output is also 180 degree phase shift. Okay, so these were the information which we studied. Okay, now this is another important thing, that we are giving input as VO sin omega t plus VCM at one end of the input, and at the another end of input we are giving minus VO sin omega t plus VCM, where VCM is the common mode voltage and VO is the amplitude of the input, and effectively we are applying something like this. So if this is my input, which is varying from plus VO side, let's call it plus VO side to minus VO, with some DC value, we are going to call it VCM, that makes one input which is something like this. Another input I am applying which is again something like this, VCM minus VO sin omega t, because there's a 180 degree phase shift. And my input which I am applying to my circuit, it's differential. So differential means it's a difference of two inputs. So the difference of two inputs, as we learn, the input should be double of the amplitude which you are applying. So effectively at the input we are applying 2 VO, not only VO. Differentially we are applying 2 VO. Although we are applying only VO at this terminal, at this terminal of Q1, but effectively combining the input of Q1 and Q2 both, the differentially you are going to see 2 VO at the input. So now moving forward, okay, this is very important thing which I should say. It's very important because now we learn that this is my differential amplifier which has two inputs. One is V in, one is minus V in, or one is VCM plus VO sin omega t, and one is VCM minus VO sin omega t. This is what I want to do in my laboratory, and I want to check how much is the output. But look, if you want to use these as a signal at the input side, do you know any instrument which will give you guarantee that there is a phase difference of 180 degree? Actually some instruments are available, some function generators basically are available, which you have to make the phase. I'm drawing the back side of the function generator, where there is some link you have to connect. This is the back side of the function generator. Function generator is, so front side is this side, and at the back there are some settings. I have seen it for Agilent that they do that, but it's very expensive. Look, if you are doing this kind of thing and if you ask Agilent to do that, so they will definitely charge lots of money. So my proposal is Can't you use something without using this solution, without giving money, and you have some cheaper solution? Maybe some, if I'm asking to my students when I'm teaching, they are saying that like I should use something like 2-function generators. When I taught this course long back to my students, they were saying that the first solution was 2-function generator. One will give you VO sin omega t, another plus VCM. So there is DC offset is available. So VCM minus VO sin omega t. This may be the solution, but the problem is how to manage the phase. 2-function generator which are independent to each other, how to make sure that these two phase will be exactly 180 degree. How can you make them in a sync? There is no like nothing you can do that. And although this solution is also very expensive because you need one more function generator. So I want the solution which is using only one function generator without adding anything extra in my function generator, and which is not costing anything to me. Means I have one function generator and that function generator should be giving me plus and minus both. So how to do that? So there is one small technique. It's very easy technique, it's ancient, everyone knows that, but I am discussing that. Technique is, let's use one transformer, and that transformer is center tapped. This center tapped voltage, let's connect it to common mode voltage or the DC voltage, right? And here if you are applying some sine wave which is 2 VO sin omega t, you are going to see here VO sin omega t and minus VO sin omega t here, right? So this is what we are going to see, and effectively it gives the guarantee that there is difference of 180 degree, and it's happening because of peak inverse voltage. Still its peak inverse voltage of this transformer is 2 VO sin omega t, but I am splitting up to with respect to VCM instead of giving with respect to ground, and my two inputs are VCM plus VO sin omega t and another is VCM minus VO sin omega, and you can use these voltages to your differential amplifier. Now it guaranteed that whatever you are going to see, it will be 180 degree phase shifted. So this is what you have to do, the center tapped. This may be one solution. Excellent. So if you understand that, let's go to common mode voltage behavior with current. So okay, so let's assume that there is circuit which has two transistors Q1 and Q2, and I am giving input which is sine wave. So it's very insightfulness, and you should understand this one very clearly. Then and then you can understand why we are making the differential structure rather than pseudo differential. This line means to bias, and I'm connecting this to here. And here there are two signals I'm giving, this sine wave and this sine wave. This sine wave and this sine wave. So what will happen at the output? Output will look like this one, maybe this one, no problem. But what will happen to this current flowing through this branch and this branch? So this current, if it is IC1, and this current if it is IC2, IC1 and IC2 both are function of input common mode voltage, or we can call it, it's a function of inputs. As input is changing, my current is also changing, which is very bad, because we learn that our circuit has to be PVT independent. My current is dependency of voltage. It may be linear, but still it has a voltage dependency. We remove the dependency of process and temperature. If you remember correctly, we have not removed the dependency of voltage. right? So I want to remove that dependency. So that is what I'm writing here, that your common mode voltage is changing, common mode voltage changes the current with respect to its own voltage. So if input is moving, current is also moving and it's in the same direction. So it's like linearly increasing, but still it's not a good thing. It has to be stable at one point. Then and then I can design my circuit. So what I want to say as some salient features of, if I want to introduce differential structure instead of pseudo differential, what were the problems in pseudo differential and how to solve it, that is given in this slide. So what I am saying is, your common mode voltage varies and it varies the bias current, which is wrong. We don't want that. So simple modification yield an elegant and versatile topology, which is called differential structure. The differential structure is the one where you are connecting or you are tying Q1 and Q2. So in this topology, I am going to remove this part, and simple one thing I am going to add. I am going to add one current source. Let's name it as IEE. So now if I do this, what will happen? So this is differential structure. Now this part of the circuit has a relation with this part of circuit. They are interacting each other, and interaction is good in such a way that there is a loose control of voltage. The voltage control is there, but it makes sure that whenever there is a voltage is sufficient enough to make your Q1 and Q2 both the transistor in active, its role is over. Means my common mode voltage, when my common mode voltage is sufficient enough to make these two transistors in active region, when I am drawing this green color, means they are in active region, means the collector current flowing through both the side will be equal. IC1 and IC2 are equal, and they have to be equal to IEE by 2 if my common mode voltage is equal, because it has to follow the KCL. If I am, my current sink is asking for the current of IEE, both the transistor are the slave of this current source and they have to supply the current of IEE by 2 or maybe in total of IEE. So if one of the VCMI is more and another VCMI is smaller, maybe the current distribution will be different. IC1 may be higher than IC2 or IC2 may be higher than IC1, or maybe both are equal, but at the end of the day the addition of both will be equal to IEE, because that's the KCL. It has to follow the KCL. So this is what I want to say, that if you are doing this, then this elegant and versatile structure is known as differential structure. Okay, I am seeing that there are two questions from PCPY Batma and PCPY Batma again. So what if VCM is not equal to input? Okay, good question. So that's a part of our, so you will see what if the VCM is not equal in to the input. We are going to see that in the next 2-3 slides itself. And can the differential input to be fed to a single-ended amplifier? No. Then it's not differential, then it's not single-ended circuit at all. Maybe you have to little bit change it, and at the end whatever the circuit you are seeing, it's differential circuit. So that circuit will not be known as a single-ended at all afterward. Okay, so let's go back to what we were started. So we have reached at the level where what is the differential structure, and differential structure is the one where both the emitter are connected to each other or tied to each other, and we are putting one tail current source, and the role of this tail current source is that it has a loose control from the common mode side. So just the common mode input is the one which makes sure that your transistor is in active mode of operation. That's it, right? So this is what we wanted to do. Now this is the differential mode of structure which we got from the common emitters circuit, and we have added one extra current sink at the down, and we are going to call it IE. Okay. So in this circuit, now let's draw this circuit again because it's very important. Okay, so the circuit is as follows. So you should assume that I am also giving DC voltage, and it's in that case what is happening. Okay, sorry. Okay. Both are connected through one voltage called VCM. So just after this understanding, we'll go to the point when what will happen if common mode is not same. This is what we are going to study just after this. But the first part is if both are equal, what is happening. So let's do the quantitative analysis where our assumptions are both the transistors are equal, both the resistances are equal, and if we are doing that, then VBE1 is equal to VBE2. Let's call this one as RC for better understanding. And both the transistors are equal, then VBE1 and VBE2 will be equal. Similarly, the current flowing through both the sides, IC1 and IC2, are also equal. Let's call them IC. And V out, looking at both the side, or the VC, both are also equal. We can say that V out is equal to VCC minus ICRC. If you are applying the common mode voltage, which is same, what will happen? The collector current which is flowing, it's equal to VCC minus IE by 2 times RC. Right? This is what you are going to get at the output side, or it's the collector to emitter voltage. We can call this one also. Right? So now my one main concern of whole study is my transistor should be in active. So when my transistor will be inactive, my base to emitter junction is in forward bias and base to collector junction is in reverse bias. And this can be only done when this potential is plus, this potential is minus, and this potential is plus plus. What do you mean by this plus 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 and minus? Means this potential must be higher than this potential and this potential must be higher than this one. This is what I am giving the notation this way. So if I want to do that, then I should make sure that this voltage has to be greater than my input, and my input is VCM. So this is one one condition I got. If I want to make my transistor in active mode, I should keep at least this number, which is VCC minus IE by 2 times RC, greater than or equal to common mode voltage, or the common mode voltage has to be designed such a way that it's lesser than or equal to VCC minus IE by 2 times RC. If I can do that, my transistor is in active mode. There is no problem. Yeah. So I kept one numerical for that. That numerical is, if there is a bipolar differential amplifier which employs the resistance of 1 kilo ohm and the load current of 1 milliampere, then how much of common mode voltage should be applied to the circuit? So that is depending from the equation which we have derived just now. It's VCC minus VCM should be greater than or equal to RC times RC times IE by 2, and it's equal to 0.5 volt. If you put up these values here, and in our case, if you want to find out exact number of common mode, you should know the VCC. So if I'll tell you that VCC is equal to 2.5, then you know that okay, it has to be in the range of 2, right? That you can find out. So to know the exact value of common mode, VCC should be known. So in this case, I have not given VCC. That's why I have derived in terms of VCC minus VCM. So difference between VCC and VCM should be more than 0.5 volt. That is the meaning of this. Okay. Now for the same thing where there is a common mode voltage I applied just now as an input, what is happening at the output common mode voltage? So the current flow through both the transistor does not change with input common mode voltage. This is one thing. Another thing is output reject common mode input or interference or the variations that will be nullified, whether it's coming from this VCC or it's coming from input common mode, because in both the cases we are going to take the differential amplifier, or if it is a difference of two quantities, then you are not going to see any common mode noise, or there is no interferences, or there is no variations. So it's a good part, and it's a second part of that. So differential amplifier, in another way around, you can call it, it has a better capability for rejecting the common mode. It's very popular term to quantify that my differential amplifier is good or not. It's depending on something called common mode rejection ratio, and that is defined as two quantities, A differential divided by A common mode, where A is the gain. So this will tell you, so as your common mode is rejected and there is zero gain, means when you are rejecting and there is no common mode, then your common mode rejection ratio is tending to infinity. This is what we are expecting, and this is what we have just proved also, that if you are having the differential structure with one assumption that both the balanced blocks exactly identical. If they are not identical, it's not going to be the same thing. So Q1 and Q2 has to be equal, RC1 and RC2 has to be equal. If this is the case, if you can achieve that, somehow your even harmonics is 0 and your common mode rejection completely is 0. So it's a very good thing. Your common mode will be rejected, your even harmonics will be removed, and your circuit is like having the better signal to noise ratio, and your tail current guarantees for current flowing through Q1 and Q2. So this is good part of differential circuit over pseudo differential. Now let's look at the question which just now we got from one college, and they are saying that what if the common mode voltage or the DC voltage at input side Q1 and Q2 are not equal. So I am keeping one condition, condition when they are not equal. What I have done, I am drawing this transistor down, means it has a lower value of input. This is the meaning of, so that people can understand it like visually, that this potential which I am applying here, if it is plus 1 volt, and if I am applying here which is 2 volt, or VCC is 2.5 volt, and this is 0, and then I am interested in output. Still the condition is same, Q1 and Q2 are same, RC1 and RC2 are same. If they are not same, you cannot make good differential circuit. But on paper, let's assume that everything is equal and everything is balanced. In that case, what is going to happen? So if I am applying plus 2 volt here and I am applying plus 1 volt here, what will happen? The this transistor, as it has a plus 2 volt, and let's assume that for a plus 2 volt, this Q1 transistor carries entire current, which is IEE. If entire current will be supplied by Q1 itself, means IE has been satisfied, then this side Q2 should give only 0 current, and this is only happening when this is open circuit. If there is open circuit, so there is no connection actually. So let's look at 2 points, one is Vx and one is Vy. So clearly Vy is equal to Vcc, and why it's happening, just look at this side, it's Rc2, this side I am applying Vcc, and this is Vy, and I am checking on my multimeter. Let's say I am using multimeter, and that multimeter has some resistance of R mult, and generally it's very high. Generally it's 1 mega ohm or maybe more than 1 mega ohm. If it is very high, then you should see exactly Vcc over here. And how? You can, if you want, you can write down these equations like R mult by R mult plus Rc2, and if this is infinity, then I am dividing with R mult, so you can see. So Vy is exactly Vcc. If my measuring device is not faulty and it has input impedance is infinite, then I can see directly Vcc. So I am assuming that also, that my impedance of multimeter is also infinity. Then I am going to see here Vcc. Now I am worried about Vx, because Vx is more important than that side. So at Vx, as there is a branch, look like this one. The current flowing through this one is IE, and I am measuring, so it's the same branch, so current flowing through this resistance will be IE, and the voltage drop across this one will be IEE times RC, and the voltage applied here is Vcc, and if I am measuring the voltage at this node, Vx is equal to Vcc minus Rc times IEE. This is going to happen if one side is very high and another side is very low. Maybe I can make it in a better way. Let's assume that, so let's take all the cases together rather than going. So one case may be when this transistor is higher, means it has more voltage than this voltage. This is the meaning of this one. It's a lighter, maybe 1 volt, and this is 2 volt, 2.5 volt, whatever it's there. Another condition is this is down and this is at up. So applied voltage here is lighter. For Q1 it's lighter, for Q2 it's lighter. And there may be another condition where both the inputs are exactly equal. So nothing is lighter. So there are 3 possibilities, and there is a, of course, you should assume that there is a tail current is already connected. It's not pseudo. Question is also there. Yes. Okay. So thank you for this question. That does the temperature affect the current IE, hence change the active region of Q1 and Q2? Yes, of course, it will change. So for that, if I am using just a resistance over here, which is asking for some current, and if that is the case, then this is not, this is dependent on temperature, of course. But if I don't want the temperature effect, then I have to use something called current mirror. So to solve this, you have to use current mirror circuit at the bottom rather than, so unfortunately it's not part of this course, but I'm just drawing for you. If you can understand, it's good. So this is a circuit you should put. Instead of the current mirror where I am drawing this kind of circuit or this kind of source IEE, this circuit will solve your problem of temperature dependency. There is no temperature dependency and it will not change. The current will not change and your common mode will not change. This is the circuit you should use for answering your question. Okay, so let's get back to what we were talking about. And similarly, yeah, somebody asked last time that how to amplify the DC current. If you want to amplify the DC current, then you have to use current mirror circuit where you need to add multiple transistors in parallel, or you need to increase the area of your BJT. That's how you can increase the DC current flowing through the another branch. So that's what you can do. So now let's get back to our discussion where we had three cases. In one case Q1 is higher than Q2 and Q2, another case Q2 is higher than Q1, and one case where both are equal. So let's assume that you are applying an input which is V in 1 minus V in 2, where V in 1 and V in 2, this is more than, let's say, V in 1 minus V in 2, that subtraction quantity is very high, or plus means V in 1 is very high. In that case, what is happening? The current flowing through Q1, this is V in 1 by the way, and this is V in 2. So in this case, current flowing through this one will be completely IEE, and the current flowing through this part will be 0. There is another question. Can in AC and DC be simultaneously applied to pseudo? Yes, of course. You can apply AC and DC simultaneously, but when we are doing the analysis, in that analysis we are treating one source at a time, so that you can apply superposition theorem. So this is what right now we are doing. We are finding out what is the small signal gain, or what is the common mode gain, and what is the common mode behavior. Those kind of things we are treating separately. So although right now we are only adding some plus and minus, which is DC values right now, after that we are going to add something called sine wave. So on paper we are going to do AC and DC separately, but by principle on experiment you have to apply both the things together, otherwise this will not work. Yep. So this is for just for easy understanding, I kept it separately. Okay, so let's get back to our work where V in 1 and V in minus V in 1 and V in 2 are the difference quantity which I am giving as an input, and V in 1 is very high, so it's available this side. It's at the positive, this is 0 and this is positive side and this is negative side. Let's assume that this is minus 2.5 and this is plus 2.5. So if I apply V in 1 as plus some big number, then the all current is flowing through this one, and I am drawing the current value. So current will be IEE, right? And when both are equal, this current is IEE by 2. So difference of V in 1 and V in 2 both are 0, then the current flowing through both the branches will be IE by 2, right? Sorry, I made a mistake. I should have drawn this way. It's IE by 2, and when this V in 1 quantity is very low, in this case V in 1 is lower than V in 2, then there is no current flowing through this one and it's 0. So if you plot it, it looks like this one for collector current for Q1 transistor. Similarly for collector current IC2 for Q2 transistor will look like this one. When V in 1 minus V in very small number, then the current, all the current is flowing through this one, and this side it's 0, right? So this is what has been drawn here. In this case, you can see that the plot are coinciding each other when V in 1 minus V in 2 are equal, and the current is ranging from 0 to IE, and the total of both the currents remain same, which is IE all the time. Okay, as many number of differential amplifiers as many you want, and you can increase the gain. So if you, I believe you are talking about the just cascade, not cascode. If it is cascode, you can do as many number of amplifiers you want. The only thing is, one stage will give you bandwidth limitation. So that's what the understanding of that will be in the lecture number 3. If you want to cascade how many number of amplifiers, it depending on that. So if your bandwidth is not limitation, and if you want to achieve only the gain, then you have to, then you can add as many number of stages you want, you can do that, no problem. So why coupling capacitors are not used in differential amplifiers? Yes, they are used. They are used in differential amplifiers. We are using the coupling capacitors. Look at the question. So yes, coupling capacitor we can add in differential amplifier as well. There is no harm in keeping that. If you know that your function generator has 50 ohm and it's creating a problem for you, then okay, so what is the significance of input impedance? Okay, that's what very important. But yeah, so as one guy has asked very good question, it's called, what is significance of input impedance? Okay, so very quickly I'll tell you what is the significance and why it's used. Let's assume that you are having one circuit which is called voltage control voltage source. Voltage control voltage source is the circuit whose input is voltage, output is voltage, and this quantity can be identified as a voltage or current. It's depending on the impedance. First of all, it's depending on the impedance, and how it's going to be told maybe in 1 or 2 minutes how it's been done. So input side it's input impedance, output side it's output impedance. Let's forget that there is some quantity called voltage, and as we agree that all the circuit has some input resistance, all the circuit has some output resistance, and if I am connecting this circuit 1 with circuit 2, it may have input resistance and this may have output resistance also. Now let's assume that all the wire resistance is equal to 50 ohm. So if I am connecting this circuit with one wire which is 50 ohm, and before connecting this, the voltage here, assume that it was 1 volt. This voltage is 1 volt. So the voltage available at this point, if this is V2, V2 is equal to Rin by Rin plus 50 times V1. This is what we have. So what should be the condition of Rin so that V1 and V2 are equal? So that only can be done if Rin is equal to infinity. If Rin is infinity, maybe you can divide the whole thing with Rin, and at the end what you are going to see is this one, 1 by 1 by 50 by Rin. So if Rin is infinity, then this term goes to 0 and your V1 equal to V2. So if I have any circuit whose input is voltage, and if I don't want that to be loaded by the previous circuit, I should make sure that that input impedance of any voltage circuit has to be infinity. This is one thing. And similarly, if you are talking about R out, look, whatever the circuit I am connecting, if I make, for a safety side, if I make this one as low as 0, then there is no problem. That this itself is 0, and for the 0 resistance this is giving me 1 volt, or maybe very low voltage, low resistance, it's giving me 1 volt. Then even if I connect anything to that, this will give me, so even if this is low resistance, still I am going to see the V1 equal to V2. This is what going to happen. So if it is voltage control voltage source, voltage control current source, current control voltage source, and current control current source, all four are categorized in such a way that they are depending only on input impedance and output impedance. Just now we learned that input impedance for VCVS has to be infinity and 0. For this one, so you have to derive it. For this one it's infinity, and for this one also infinity. For this one it's 0, and voltage side it's 0. This has to be 0 and this has to be infinity. So if it follows this condition, then your, let's say for our case, when we started, our circuit's input impedance was infinity and output impedance was 0. So that circuit was voltage control voltage source. However, for BJT, whose small signal model looks like this one, if I see from the input side, by connecting everything else as a ground, I am going to see R pi at the input side. If I look from output side, by keeping this as a short to ground as an input side, so if this is 0, this is 0, VBE becomes 0, so whole quantity becomes 0. So if I am looking from this side, the current is 0, means I am seeing the open circuit. When it's open circuit, output impedance is infinity. So you can see there are two values are coming. One is Zin equal to R pi, Z out equal to infinity. When Zin equal to R pi, means R pi is in range of 1 kilo ohm and we call it low. Similarly, this is infinity. So let's look at this matrix where your input impedance is 0 and output impedance is infinity. It comes under category called current control current source, or CCCS. Means your BJT is CCCS. So similarly, you can derive it for other circuits and you can find out what your circuit is, and that is the role of your input and output impedance. And I believe I answered your question. Okay, so yeah, so we were here and talking about these curves. So in these curves we found out that, oh okay, so instead of that instead of the current, if you are measuring the voltage, your voltage will be varying from VCC to VCC minus RC times IE, and at the middle voltage, when both are equal, or V in 1 equal to V in 2, then your output voltage Vx and Vy both will be equal, and that will be equal to VCC minus RC times IE by 2. Okay, so this was the one story. Now, okay, somebody has questioned that AC and DC can be applied together. So in this circuit, I am applying AC plus DC together, or maybe you can call it, I am giving common mode voltage, and on top of it I am giving some small signal input. Small signal, you know what is small signal, it's not going to saturate your output, means it's going to call as small signal. So let's assume that you are not giving any signal which is saturating the output, then that is a small signal and it's small enough that you can see the amplification. So in that case, if there is input of VCM plus V one side and there is VCM minus delta V one side, then what is going to happen? Effectively, you can see that the current flowing through Q1 and the current flowing through Q2, which will be equal to IE by 2 plus delta I and IE by 2 minus delta I respectively, which is written on the left side of the slide. You can see that, right? And if I am looking at the current, which is delta change, look, I am interested in delta I because that is delta is a small change, and that small change I want to find out how much that reflecting as a voltage gain or that is reflecting as a current change. So delta I, if I am applying some input voltage, at the application of input voltage, you can see here, if I apply something at VBE, my current which is varying, it has to be GM times VBE. Just look at that. If I am applying the voltage at input, which is right now VCM plus delta V, one transistor. If we are looking at only one transistor, then the current flow through collector will be GM times VBE, and that VBE is equal to this base voltage minus this P node voltage. So that is what I am writing here, that delta IC1 is equal to GM times VBE, where base voltage is connected to delta V and emitter voltage is connected to delta VP. Similarly, for delta IC2, if you are writing, it's GM times VBE, where base is connected to minus delta V and VP is connected to delta VP, and the effective current will be equal to GM times minus delta V minus delta VP. So you can take minus outside and you can have effectively minus GM times delta V plus delta VP. If you equate both the currents, you will see that the delta VP is equal to 0, or you can say that from where our discussion has started with the just by the observation that if we are applying the voltages which are 180-degree phase shifted to each other, or one side if you are apply plus voltage and one side if you are apply minus voltage, you are going to see the link voltage as a 0. So that node P is a ground, or it's known as the virtual ground, or it's virtually AC ground. This is what we are going to see, and that is proved by this analysis. Now let's go to the next part, where you already know that delta IC1 is equal to GM times delta V, because now delta VP is 0. So in this equation, previous equation, put delta VP equal to 0 in the first equation. So effectively delta IC1 equal to GM times delta V, delta IC2 is equal to minus GM times delta V, and for a given GM and delta V, your delta Vx, which is output at node X, which is output node, is equal to minus GM times delta V times RC. If you look at the circuit, one side, if this is VCC, this is RC, the delta change here, delta V, sorry, I should say, the delta I is equal to GM times delta V, and voltage drop here will be GM times delta V times RC. There is no change happening at VCC, so I am not taking into account because derivative of that one is 0. So it's gone. It's not useful. Here, same thing is written here, minus GM times delta V times RC, and VCC is not, there is no change by VCC with respect to delta X, so there is not important term right now. So it's minus GM times delta V times RC, and delta Vy is equal to GM times delta V times RC. It's a opposite polarity which we have got for Vx. If you take the subtraction of both the side, you will get minus 2 GM times delta V times RC, and if you find out the gain at the end, you should see minus GM times RC. Okay, this is the one crux of the story, that your gain, voltage gain, is equal to minus GM times RC at the application of input, which is double now. Is it possible any circuit is PVT independent, and if yes, so why? Yes, there are many circuits which are PVT independent. So we have to talk about it maybe independently. First of all, all the circuits are not possible to discuss, but yeah, I can talk about our circuits. So PVT independent, the current mirror is PVT independent. So for that you have to write down the current equation. So main thing was the gain is coming as minus GMRC, and if you are looking at the behavior, so the two current, the first plot is current plot, second plot is voltage plot, and the third plot is V out 1 minus V out 2, which is coming from RCIE to minus RCIE. So this is the concluding remarks for the analysis which we have done and which is useful for understanding the rest of the part. So let's see, maybe we can talk about other things maybe next time, not today will be too much for understanding, right? Somebody wants to interact? Okay.
Hello.
Yes, PCPY.
What is the real-time application of differential amplifier?
Application of? Okay, so the real-time application of differential amplifier is everywhere, whatever the circuit you are seeing, all are differential amplifier. First of all, if you are making amplifier, if you are making something called comparator, if you are making ADC, if you are making any circuit which needs amplifier, you are going to use only and only differential amplifier, because look, most of the time if it is communication application or maybe any other application where you are sending some signal, it will not be linear always, or you can say it will not follow the linear equation which is y equal to mx plus c. It will have always some non-linearity, or it will have harmonics, and you don't want those harmonics. Those harmonics are measured in terms of signal to noise ratio or maybe the total harmonic distortion. So if you want to reduce them, you should always use differential structure, nothing else. Yeah, do they want to ask any other question? PCPY?
Okay.
Okay, thank you. DGI Sunil, good morning.
What is the significance of small signal analysis?
Okay, so small signal analysis is the one which is telling you how much gain is available from your circuit. If you remember previous lecture, we agree that if your input is not small enough, and if that is the case, then the output will be saturated, or you will reach the VCC, right, or you will reach the ground. And let's say if I am applying 14 volt of input and my VCC is 15 volt, then like I am not going to see anything, it will be saturated output. But if I give very small input, let's say 0.01, and my gain is 100, then I am going to see 0.1 at the output. So small signal is the one which gives me the exact number of gain. Moreover, it's going to tell me that what is the bandwidth limitation. Okay, so those things, bandwidth limitation, we are going to study in lecture number 3. But small signal analysis will give you, the first part is gain, the accurate gain value.
Thank you, sir.
Thank you. Thank you. In question in chat. Okay. Okay. What is Ebermole's equation? But you didn't reply. Okay. So this is another way of, look, in every device there are different way of model it. First of all, so there is one something called BSIM. You have heard about Berkeley simulation model. So in that there are they are using different kinds of model, and every scientist, every mathematician, every person is giving its own model which has temperature, it may have threshold voltage. The one which we are using is the most simplest one. The current equation which we have used is the simplest one, but Ebermole model is a different and given by different person. Okay, so that is, look, this course is not for compact modeling of BJT, but yes, of course, if you know that equation, through that equation also you can do all the analysis which we have done, right? So that is what the role of Eber-Moore. If you like that model, you can do that also. Yes, please
So,
ask the question. Yes.
so good morning, good afternoon, sir.
Good afternoon.
So, why are the event components should be removed from the signal, sir?
Look, the main problem in anything, if you are using as a, let's say, communication application, then if you want your signal, you don't want anything which is distorted. What I mean by distorted is, let's say you are talking to your friend on mobile, you are sending your
Yes.
speech signal and it's getting received at the another end, and he is only listening your voice. But if that voice is distorted, means it's riding with another signal. Another signal means somebody else is talking and that is riding there. So it's not a good thing. So just now we have seen something like echoing the system, right? So those problems are because of bad signal to noise ratio. There is signal to noise ratio is bad, means it has all the harmonics, even harmonics, odd harmonics, even common mode noise, all are available. And you want only the fundamental, you don't need anything else. This is the first first thing, right? So we have removed even harmonics, but moreover we want the odd harmonics also to be removed, but odd is not available right now. How to remove that? We can like, it's an advanced course of BJT where you can learn the different techniques, but at the first hand the differential structure is used for removing even harmonics. Yeah,
Okay, sir.
that's how you are making the SNR better and better.
Okay, sir. Thank you,
Any
sir.
other question? Yeah, thank you for the question. Any other question? If no question, then we can leave. Okay, I can. Okay, thank you very much. So I'm signing off for today. Thank you for listening to me. Thank you.